Hi there, and welcome to the chapter that will take us further from cells to modules, rack, and enclosures. And we'll start from modules. So, first question we might ask ourselves: how many cells should be inside one module? And the honest answer is there is no single perfect number. It's always a trade-off between electrical design, like electrical code compliance, manufacturing, and serviceability. And let's look into these parameters in more details. But first, we need to understand the main concept. For this, we'll look inside through the lens of Six Sigma and lean manufacturing, and not just battery chemistry lens. In lean manufacturing, we have a waste, and waste is anything that does not create value for the customer, but still consume cost, mass, volume, or time. In battery system, inactive materials are exactly that kind of waste. At the material level, almost everything is adding value. Active materials store energy. That's core function of the battery. But as soon as we move to the electrode level, we have add binders and conductive additives. These don't store energy, but they are necessary to make the product manufacturable and reliable. From lean perspective, this is necessary waste. We accept it, but we try to minimize it. At a cell level, the amount of waste increases. Casting, current collector, separators, electrolyte, and safety features add cost, weight, and volume, but no energy. Again, they are required, but they reduce gravimetric or volumetric efficiency. When we move later to pack system level, we add even more non-value adding elements. Cooling system, bus bars and wiring, BMS electronics, mechanical frames and enclosures. All these increase cost per kilowatt hour and reduce system efficiency. Finally, at the application level, such as battery energy storage container, the amount of inactive material is at the highest. Containers, HVAC, fire protection, controls, auxiliaries, and they are critical for safety and operations, but from the lean point of view, they are still waste. This explains why only about 20 or 30% of the final system mass or volume is actually storing energy, and we have a lot of additional costs that don't bring any value to us. So the idea is battery innovation is not only about battery chemistry, it's also about reducing waste at every integration level. We already touched it when we were talking about 5 and 6 MWh containers. And we'll start with electrical density. And you remember this formula early on, and we refer it quite often. Energy equals power multiplied by time, and power is voltage multiplied by current. That means if we want to more power or energy, we have two main levels. We can increase current or we can increase voltage. In large battery system, increasing current quickly becomes expensive and inefficient. Thicker cables, higher losses, more heat. So from a system design perspective, we prefer to increase voltage. But higher voltage at the same time means a more dangerous system. That's where standards set hard limits. So international electrical safety standards clearly defined where low voltage ends. You can see IEC 61140, which is the root document for electrical shock protection, defines low voltage as up to 1000 volts AC or 1500 volts DC. And the rest of the standards do the same. In the United States, North America Electrical Code, or NEC, and exactly NFPA 70 align with this practice, and systems about 1500 volts DC fall into different category with much stricter rules, barriers, training, and clearances. So the key takeaway is simple: 1500 volts DC is this number, and it's not a random number, it's a standards boundary. Now let's translate it into cells and module design. On the right, you can see typical LFP cell voltage curve. What it means? It means depending on the battery state of charge, what will be our voltage. And at 3.2 volts, it's nominal LFP cell voltage. And it operates between 2.5 and 3.55 volts. So if we take the maximum cell voltage, because standards always care about the worst case scenario, and divide 1500 by 3.55 volts, we got about 422 cells. We need to keep margins for safety, temperature effects, and tolerances, so the industry typically uses 460 cells in series. That give us 3.55 volts multiplied by 416, it's around 1477 volts. It's safely a little bit below the 1500 DC limit. That's why you often will see that 416 cells in series is a standard configuration for 300 ampere hours LFP based BESS designs. And the same will be for future generation based on LFP. As we discussed how series and parallel connections affect performance in fundamentals part of this course. Once the series count is fixed by voltage and standards, the rest is straightforward. We add parallel strings to increase capacity and energy per enclosure. So, voltage defines the series count. Standards define the maximum allowed limit. The system energy is scaled by adding parallel paths. This is a great example of how standards quietly shared hardware architecture, long before anyone talks about container size or megawatt hours.